webinar speaker is Anders Petersson. Anders earned his PhD in numerical analysis from the Royal Institute of Technology in Stockholm, Sweden. He joined the Lawrence Livermore National Lab in 1999 and currently works in the Applied Mathematics Group in the Center for Applied Scientific Computing. His research interests lie in the area of grid generation and numerical solutions of partial differential equations. Anders currently works on the Serpentine Wave Propagation Project along with Bjorns Sjogreen, Hans Otto Kreis, and Artie Rogers. Methods developed for the project have been implemented into SW4, which he is here to talk to us about today. So without further ado, Anders, the connection is all yours.
Okay, thank you very much, Lorraine. I hope everyone can hear me. So, thank you for that nice introduction. So, as Lorraine mentioned, I've been at Lawrence Livermore since 1999, so it's 16 years today, almost in today. So anyway, I'm going to talk about SW4. This is a parallel simulation code for seismic wave propagation. It's open source and it's hosted by CRG, as probably most of you know. And this code grew out of a project that's been going for almost 10 years now. Our first code was called WPP. That was second order accurate. So this is the successor of WPP, and we call it SW4 for seismic waves, fourth order. So today I'm going to talk about what's inside SW4, and also I'm going to talk about how we use SW4 to set up the simulation and various features that we provide. And then I'm going to say something about how you run it and make some practical suggestions. And I think the best thing is to keep the questions to at the end. But if you have something you want to ask me, you can always type into the chat window. So here we go. So SW4 is a time-dependent code. So it's the 3D visco-elastic wave equation. It uses something called summation by parts finite difference method. It's fourth order accurate in space and time, and the summation by parts that I will go into some detail on the next slide has this feature that it's an energy stable method. So regardless of how crazy your material is, the method is stable as long as the time step is clear. So we focus on local and regional simulations. So it's up to a couple of 100 kilometers from a seismic event. So the equations are solved in Cartesian coordinates, and we use a projection from the geographical coordinates to our Cartesian coordinates that we use in the code. So this neglects the curvature of the Earth. So if you want to solve wave propagation in a domain that is larger than, say, 500 kilometers in the horizontal direction, this is not the code for you. So we can deal with elastic or visco-elastic material models. The basic model is an isotropic elastic material, and we assume that the shear modulus is greater than 0 everywhere, and also that the first MA parameter is greater than 0, and of course the density has to be positive. And we can also model viscoelastic attenuation, and that is described by the quality factors QP and QS for attenuation of the P and S waves. And they are modeled as approximately constant in the frequency domain. There's also a new feature in SW4 that was implemented a couple of months ago that allows you to do fully anisotropic materials in a 21 parameter model. We can do curvilinear coordinates, and we use that to model realistic topography. And one nice feature of SW4 is that you just have to provide the topography information in the file, and then the mesh is generated almost automatically. And this is done in a pre-processing step before the solution starts. So I'll go into more detail about that later. The curvilinear coordinates are also used to construct supergrid absorbing far field layers. And they are of PML quality, but the advantage of supergrid is that it also works for complicated things like anisotropic materials without any stability issues. So our source model is kinematic, and we allow for moment tensor sources and or point forces, or both. And you can have many of them, and you can have many different time functions. So I'll mention a few of them. And if you have very complex ruptures, you can describe it in a so-called SRF file, version 1.0. That is a file format described by the sketch web page of it. So after you run SW4, you can produce many types of outputs. For instance, the time series at various receiver locations, and you can also have cross sections of the solution or the material properties in so-called image files. And SW4 can also make GMT scripts to plot out the computational domain and all receivers and sources on and on. So one feature that I was hoping that I'd be able to tell you that it's all available now, it's almost done. Yeah, we have a local mesh refinement in the works, and that's coming soon. So moving on here. So what is summation by parts? If you write the elastic wave equation as a partial differential equation in second order form, it means that you have second derivative. You get this familiar form at the top here, where LU is the divergence of the stress tensor. Now, you can discretize this on a computational grid, and then this variable B is the discrete version of the variable U above. And then you approximate the spatial operator, L, with something, a discrete operator called L sub H. And summation by parts, that gives L sub H desirable properties such that it's symmetric and negative definite. And that's where this energy stability comes from. So if you want to hear more about summation by parts, you can check out our papers that we have on our web page listed below here. So I'm from Sweden, so SW4 therefore uses SI units, meters, kilometers, seconds, and everything is derived from there. And all the angles are in degrees. So essentially, the basic version of SW4 uses a box-shaped computational domain, and the z-coordinate points downwards into the Earth. It's a right-handed system. So optionally, the top surface can be made to follow a realistic topography. And by default, the top surface is subject to free surface band recognition, and all other sides have a supergrid absorbing layer attached to them automatically. So here's something to remember if you use SW4. So the default thickness of these supergrid layers is 30 grid points. This means that the smallest Cartesian mesh you can have is 60 by 60 by 30. If you make it smaller than that, you're going to run into trouble. So the idea here is to do the actual calculation in this white area, as there's all sources and receivers in the interior. And the supergrid layers are the red and blue and purple parts. So you put all your sources and all your receivers in the white domain. Now, you can either specify locations in this Cartesian, directly in the Cartesian coordinates, or you can do it in geographic coordinates in terms of latitude, longitude, and depth. And then you use a mapping to map between the two. By default, we use a simple spheroidal projection, but you can also use the Prod 4 library to get better, more accurate projections. It's also possible to rotate the grid with an azimuth. So you specify where the origin is on the of the Cartesian grid. And if the azimuth is 0, then our x-axis points north and the y-axis points east. And C points straight down, as I mentioned before. Or you can rotate it to better cover the domain of interest in the particular case you want to know. Okay, so SW4, or the SW4 run is described by the input file. So here I have a very simple example here. In this case, the input file is called seismic.in. You can give the input file any extension you want to, but it needs to be a text file, and that follows the syntax that's described in detail in the user's guide. So in this simple example, the first command is file IO, and it just tells SW4 in which subdirectory to put all its active files. So you can make this a new or an existing directory, and we'll put everything in there. The next command is a grid command, and it tells SW4 how big a domain you want to simulate. So in this case, it's 10 kilometers. Everything, all the lengths are in meters. So it's 10 kilometers in X and Y, and it's 55 kilometers deep. And the grid size in this case is 50 meters. And then the third line says that we're going to go to time 8 seconds. Now the fourth line is a material command. It's one of the material commands we support. It's called a block command. It's the simplest one. It gives the same properties throughout this block. And in this case, there are no bounds attached to the block in terms of the min and max x coordinates. So it just applies to the whole domain. So in this case, we're going to have a material with P velocity 1,732 meters per second approximately, and S velocity 1,000 meters per second, and density 1,500. And so it's required that you specify the material properties throughout the domain. Another thing that is required is that you have at least one source, and in this case, you locate it in the middle of the domain in the horizontal direction and on the surface, v equal to 0. And in this case, it's a point force with magnitude 10 to 13 Newton. So this type and this frec and T0, they specify the time function. And then in this case, we're going to record resolution using this rec command, and then we have a receiver at the x, y, and z coordinates of 6 kilometers, 8 kilometers, and on the surface. And we put the result in a file that's like the V1S. You can also get snapshots of the solution through the image command as shown here. And in this case, you say the z component of the displacement. Now running this is done by it depends on what machine you are, exactly what the command is, but often it's called MPI run. And then you tell it run on 8 processors, and then you just go. That's it. So that is the simplest possible input file for SW4. So going to some details about the sources. So we support, as I mentioned before, point forces and moment tensor sources. So they are of this type. It's a time function g of t times either a force vector times the Dirac distribution. So it's a point force or a point moment tensor source that is shown in the second equation. So a detail here is that we discretize these Dirac distributions by imposing so-called moment conditions, and that ends up being a 6 by 6 by 6 point stencil in 3D, and that allows you to place the source at a location that's independent of where the grid points are. It still gives fourth order accuracy, at least away from the actual location of the source. So there are several ways of specifying these sources. You can specify the 3 components of your force vector F, or you can specify the 6 unique component for the symmetric moment tensor with components M, I, J. You can also use the amplitude of it, the seismic moment, and then strike different rake angles according to F and Richard. We have many predefined time functions, and they're all listed in the usage guide, and they all need the frequency parameter and the start or center time. And you have to look at the details there for each particular function to see exactly how it works. Another interesting idea that is often used to model discrete Green's functions is a Dirac distribution in time. And that will trigger all the frequencies on the mesh. So without post-processing, there's going to be a lot of unresolved wiggles. And you have to filter the results to get them to So the final option, or the second final option, is to define a user-defined discrete time function. You just define a few point values and we interpolate for you. The SW4 interpolates for you. And the final option is to use an SRF file. That's the complex ruptures. And then you will set up all the point moment tensors that are needed to follow this rupture described in this file. And that includes user-defined discrete time function. And if you want to know about that, you've got to go to the SCET website and read about that format. And note that we support version 1 of this format and nothing else. So one thing that often confuses novice users of SW4 is, what is it I actually computed? So the key here is to look at the time function, what it looks like. If you have, like the first case here, it looks like a smoothed out Heaviside function that goes from 0 and then tends to 1 for long times, like the Gaussian int in this top example. That will make SW4 compute displacements at all the receivers by default. If you want velocities at all the receiver locations, you have to differentiate the output in time once, but if you want accelerations, you have to differentiate twice. So if you change this time function to be a Gaussian, so that's the derivative, time derivative of the Gaussian int, then you get velocities by default at all the receiver stations. If you want displacement, then you have to integrate in time once, and accelerations by differentiating in time once. So the key is to look at this time function and see if it starts at, they all start at 0. If it tends to a constant at long times, then we compute displacements. The SW4 computes displacements. But if it's a time function that starts at 0 and ends at 0, that integrates to something non-zero, then you compute velocities. And if you have a function that is like the derivative of the Gaussian that starts at 0, ends at 0, and integrates to 0, then you compute the accelerations by default. So it's a good idea to look at these things in detail. So probably the hardest parameter to choose when setting up in SW4 run is the grid size. And it's all based on using the appropriate number of grid points per shortest wavelength. So in a simple model, the shortest wavelength can be approximated for L min here as the minimum shear speed divided by the maximum frequency that we will solve in the calculation. And then we introduce this quantity P, which is the number of grid points per shortest wavelength. And then it's just dividing this L min by the grid size H. And it turns out that we get good accuracy in SW4 when this P min is greater than at least 6. Sometimes it needs to be greater than up to 10. It depends on the distance between the source and the receivers, and also on the material properties in some cases. So there are several options here. For instance, you can just run with whatever source and then filter the result in the job. That's perfectly fine. Or you can tweak your frequency parameter in the source time function to make sure that you only compute the solved motions. And this is desirable if you want to look at snapshots of the solution using the image command. There's a third option here, which I actually have as the second option. Use the pre-filter command. That actually filters all the source time functions before the simulation starts to make sure that you don't trigger any undersolved nodes. So it's equivalent to pre-filter the source time function or to post-filter the receiver response afterwards. The only problem with the pre-filter is that it uses an acausal filter, so you have a long tail sometimes that you have to include in your simulation, so the simulation can be a bit long. Okay, so to understand what this maximum frequency is, I recommend you look at the user's guide in section 4.4, because each type of time function has a different relation between the maximum frequency and the freq parameter, which is what we give as the input file. And we also provide some MATLAB and opcodes for analyzing the time functions and the Fourier transform model. And they are in the SW4 tools to actually the function plot and function plot. So I recommend playing with this. And reading the user's guide is always a good idea. All right. So to do realistic topography, we use curvilinear coordinates and curvilinear mapping. So it's all based on a stretching in the vertical direction. So the user has to provide what the topography, the elevation of the topography is, and then from that information we construct the mapping inside SW4. And inside SW4, the elastic wave equation is solved in curvilinear coordinates instead of the Cartesian coordinates. And then you have to take into account metric terms, and you get a slightly more complicated system to solve, so it's a little bit slower, but it's accurate. So this technique of curvilinear coordinate mappings is also used for our supergrid absorbing far field layers. And it's essentially stretches out this region in the figure on the right to be much larger than what we see here, and adds artificial dissipation to damp poorly resolved mode. So to trigger the creation of this curvilinear mesh, you use the topography command in the input file. And there are currently 4 ways to specify topography. For testing, you can use a Gaussian hill, or you can use a grid file. You specify the elevation of the topography as function of latitude and longitude. Or you can use something called an R file, which is a raster file, that I'll talk more about later. Or you can use an E3 database, which unfortunately we only have data for the San Francisco Bay Area. So when dealing with topography, it's important to remember that we use z equal to 0 to mean the mean sea level. And the only thing that the user has to help SW4 with before it can create the curvilinear grid is to pick the bottom z coordinates for this grid. And the rule of thumb is that the user has to check the range of the topography. So for example, if it ranges from 1,500 to 2,500 meters, the difference between these two is 1,000. So then the curvilinear grid should be constructed to be approximately twice that elevation below the lowest elevation. And here, one confusing thing sometimes is that elevation is regarded to be positive above mean sea level, but z points it's positive going downwards, so you got to change the sign here. So you can, I'm sure you can figure that out. So finally, I give an example of the topography command. In this case, it's a file in lat long coordinates for this alpha rocks in that purple. Okay, moving on. So the material properties have to be specified everywhere, at all the grid points in the grid. If they are not, SW4 will stop with an error message. And the material can be specified by combinations of the block, P-file, P-file, R-file, and R-file commands. And the interesting thing here, one thing to keep in mind is, different from most other commands in SW4, here the order between the command matters, because some of these commands might only specify parts of the domain. So the rule is that the last one has the highest priority. So that way you can make this beautiful flag here shown on the left using just block commands, for instance. And if you plan to use visco-elastic modeling, then that option is triggered by putting an attenuation command somewhere in the file. And if you do that, then you also have to specify these QP and QS factors throughout the domain. So in this figure, we see on the left is block commands, and then on the right is probably a P-file command that was used for this more complicated showing that. So we're very proud of our most recent material command is called R-file. And R-file is a binary file that is ideally suited for complicated heterogeneous material models with topography. So essentially, this is just a raster file. It's a header and several rectangular blocks of data. And we support byte swapping. So you can, for instance, build this model on an Intel-based machine and then use it on your IBM supercomputer without any problems. And this type of file is read using our parallel I/O library, so it allows very fast access. We've tested on up to 131,000 cores, and it runs very fast. And one nice thing about this file format is that each core in this computation only reads what it needs to know from the file. So there's no need to store extra information, which is the case, for example, in the P-file model. Because these files can tend to be large, and some modern supercomputers, they don't have very much memory on each node, and you can run into trouble because of that. Another nice feature about these files is that the resolution in space varies. So you can have a fine material model near the top of the domain and gradually portion it out as you go down. And that way you can save a lot of disk space. And this is also used these R files also include topographic information as well. And we use this, for example, to build a model of the San Francisco Bay Area shown here on the right. Okay, so if you want to use visco-elastic modeling, you got to specify quality factors here, QP and QS. And the way we do this is we try to model a constant Q absorption band solid, I think it's called. So you try to keep Q as constant as possible, but we do this in the time domain by using so-called standard linear solid mechanisms. So here the thing is that the more mechanisms you have, the more constant the Q's are going to be. But with more mechanisms, you also need more calculations and more memory, so there's a balance. And by default, we use 3 mechanisms. So when you use these, you've got to specify, tell SW4 in which frequency band you want the Q to be constant. And you do that by specifying this F-max parameter. You also have to specify at what frequency do you want your phase velocities to be agreeing with the numbers that are in the material file, because the material becomes dispersive when you have anelastic attenuation. Okay, so make it a little more practical here. We have built SW4 on everything from a laptop to some of the largest supercomputers that we have in Livermore. We have two build systems. One is based on CMake, it's probably the easiest to use. There's another one based on MIC that also works fine. It requires a little setup to tell SW4 what kind of libraries and so on. If there are details instructions in the Appendix A of the user's guide, and I recommend you look at those. So to run SW4, you have to use some kind of MPI run command, and the exact syntax depends on the type of MPI you have on your system. So in Livermore computing, we have something called the srun command, and if you have Max and OpenMPI, it's called OpenMPI run, and then on Linux boxes, sometimes it's called MPI exec, and sometimes it's called MPI run. So you got to check that your sysadmins exactly how to run MPI programs. Another important question to ask is, given a certain case you want to model, how many cores should you use? And the basic requirement here, assuming that you're willing to wait a long time, any amount of time for the calculation to finish, is that the calculation must at least fit in memory on your computer. And Appendix C of the user's guide, we have some numbers telling you approximately how much memory is needed per grid point, depending on the type of model you use. In the simplest case, being like isotropic on a Cartesian grid, and then it needs more memory if you go and include the curvilinear grid with topography, and then even more if you have a visco-elastic model. So we often use between 100,000 and 1 million grid points per core. But it's rarely limited by memory. We tend to run out of patience before we run out of memory in our calculations. So if you want to, so you tend to run at this the lower end of the spectrum. And it also depends on your machine. Excuse me. For instance, this weak scaling study was done on IBM BlueGene system, and those cores are relatively slow. So here we use fewer grid points per core, which is equal to the number of tasks here. So here on the red line on the left, we have 180,000 grid points per core and task, and the blue line is 270,000 grid points, showing that, you know, if you keep the number of grid points per core fixed as you add more cores and more grid points, it takes about the same time to take one time install weak scaling. So SW4 has very good weak scaling. It also has pretty good strong scaling. In this case, you fix the problem, and you just throw more and more cores at it to speed up the calculation. So in this case, we started with started with 64 cores, and we made a problem that just fit on 64 cores, and then we started adding cores up to 4,096. And in the end, we got a speed up in this case of about 32. So it's a factor of 2 off from ideal scaling in that case. Eventually, this timing is going to level out as you throw more and more cores in it, because the calculation will be dominated by communication and not calculations within each core. Okay, so we also provide scripts in MATLAB and Octave or Octave for reading most of the output files that SW4 produces. So, for example, the synthetic seismograms can be written in SAC format, or something we call the USGS text files. And you can read them if you have SAC files. It's most convenient to read them with a SAC program, or you can use our MATLAB and Octave scripts. all in this TS directory of the SW4 distribution. So to read cross sections that I would call image file, you can also use our scripts in the same directory. We also, SW4 can also output information in a QMT script, but then you need all the DMT programs to interpret those results. So a few words here about guidelines. I think the problem that happens the most often, someone who first starts using SW4, they want to do earthquake simulation in some domain that is several hundred kilometers in the horizontal directions and then 50 kilometers down, and they quickly end up with 10 billion grid points and 100,000 time steps. And then they run SW4 and they wonder why it didn't work. So most things in SW4 are not dependent on the actual grid size. So it's a good idea to portion out the mesh significantly and then just run SW4 on your laptop or a small cluster and then output a few images of the material model, check the output from SW4 to make sure everything looks okay and that there aren't any syntax errors in the include file. And then gradually increase the number of grid points in your calculation. This essentially works like this, that if you double the frequency content in your sources, you need to have the grid size. And that means that you double the number of grid points in each dimension. But because we're in 3D, that means that every time you double the number of grid points in each dimension, you end up with 8 times more grid points in the 3-dimensional grid. And because our time stepping is explicit, we also end up with twice the number of time steps. So if you use the same number of cores, you need 8 times the memory and 16 times the CPU time every time you double the frequency. So you can turn this to your advantage by going the other way and use a frequency that's half what you started with, or a quarter, or an eighth, and then you get an idea how the whole thing is going to scale. And it makes it easier to estimate how much resources you actually need to do the problem you really want to solve in the end. So once you scale up, there are 2 ways to go here. If you double the frequency, you use the same number of grid points per core. You need 8 times more cores. They use the same amount of memory per core, but you need twice as much CPU time because there are twice as many time steps. Or you can use 16 times the number of cores, and you get about the same CPU time, but half the memory. And eventually, this option will be flatten out because you get so few grid points per core that it doesn't speed up. So we provide several examples with the SW4 distribution in the examples directory. And as I mentioned before, many scripts are in the tools directory, and we have documentation in the doc directory, and it's also available as a PDF file from the CRG web page. So, in summary, SW4 documented open source code is available from CRG. I think we first put it there about 1 year ago. So the version 1.1 is available as a toggle from the CRG web page. If you want the newest, the latest and greatest improvements, you gotta download the source code from GitHub using Git pull. And there are instructions on the CRG web page too. If you're curious about our anisotropy modeling, we have a recent paper in General Computational Physics. You can read all about it. And as I mentioned before, pretty soon, within weeks, there will be local mesh refinement in SW4 of this type. There's no figure from the WPP code, but essentially, it's a curvilinear mesh on top, and then Cartesian meshes that are gradually portioned out with depth. And that will save you both memory and time stepping effort, because the time step can also be made larger using a mesh like this. So on the longer term, we're looking for options to port SW4 to modern heterogeneous GPU-based systems, but that's probably at least a year into the future. All right, that's all I had to say. Let me know if you have any questions.
Thank you, Anders. This is a good time for everybody to type in the questions they may have for Anders. And while you're doing that, I want to make a few announcements. We will be having a webinar next month. We typically don't do it because it's December, but we will be having one on Thursday, December the 3rd. And again, that will be featuring Casey Schultz and Virtual Quake. We'll also be, during AGU, we'll be having our annual business meeting, so please come by the Intercontinental San Francisco on Monday, December the 14th. Information on this and all the other events can be found on our website at geodynamics.org, including the recordings of all our past webinars. Okay, so we have a couple of questions there. I think you can read them, Anders.
Okay, let's see here. I can scroll up. There are many questions. So someone asked how we define the mesh dimension. So that's used, it's in the input file. Let me see here. It's in the grid command. So here it's the second command here, h equals 50 in this case. That's how you define the grid size in the Cartesian grid. The grid size in the curvilinear grid will be the same in the horizontal direction. They will vary a little bit in the vertical direction because of the stretching rules. So let's see here. The next question is, someone wants to know about hysteretic behavior for some materials. I am not quite sure exactly what that's Lucas John. If you can further specify exactly what it is you're after. And I'll come back to that one. Let's see. Ralph Stevens wants to know about fluid layers. Well, unfortunately, no. Right now, it all has to be solids. We are working in another project to couple this to wave propagation in the atmosphere, and that solves the linearized Euler equations in an ideal gas. So that's obviously a case where you have zero shear modules, but it's not available right now in SW4. And the next question by G. Lee says something about only kinematic solution. So I assume that it relates to the source modeling. It's true, it's a kinematic source model, and that's what we support right now. Okay, so Ilya asked another question related to fluid-solid interaction, and as it is today, SW4 does not model wave propagation in fluids. So right now we can't do that. So then someone asked about SIF format, about how you calculate the slip velocity at each time step. I recommend you look at the SCEC webpage and all the information they have there about the SIF formats. It's pretty well described in there, and we kind of take it as input and we don't really do anything with it. So I recommend you look at that. See if there are any more questions here. I'm just typing. All right. Okay, let's see here. So someone asked here about the advantages of SW4 over the SCM code like Spectrum. Well, one thing that SW4 does for you in a very straightforward way is mesh generation. So this is all done as the simulation starts. So the mesh is generated automatically by SW4, while if you use any of these spectral element codes, you first have to make a mesh, and then you have to distribute that over a parallel calculation. So that's a separate step that you can avoid by using SW4.
It may be that SW4 handles anisotropy better as well.
Well, that is possible. I mean, I don't think there's anything that stops anisotropy from being implemented in the spectral element method.
Yeah.
Whether it's implemented in SpecFem, I don't know.
Yeah, that and attenuation.
Someone asked here if we can define sources as force couples and define the source as generalized moment tensor. Well, I'm not sure what you mean by generalized moment tensor. You can certainly have many point forces, and you can manually make a moment tensor source using forces if you want to, but I'm not sure why you want to do that. So Ilya asked a question here, what's the maximum number of nodes that the model can handle? So I think that depends on how large your machine is. The largest mesh we have used had 65 billion grid points, and it was ran on 131,000 cores on IBM machine in Livermore. I don't think there's any upper limit. It just depends on what kind of machine you have access to. So any more questions? Now's the time.
I'm interested in this question that Lucas was asking about hysteresis, so maybe he can clarify whether that means time-dependent material and what sort of, if he can provide an example.
Yeah, I'm not sure exactly what he means by that. But the model, the material model is time independent as it is implemented in SW4. If that answers his question, I don't know.
It says strain-dependent shear modulus reduction.
I am not sure if you can capture that with the standard linear solid elements that we use. I'm not really an expert at material science, so I would have to get back to him with a precise answer about that. Okay, so then there's a new question about mesh quality. So the mesh, in general, the quality of the curvilinear mesh will be improved if you make the curvilinear mesh thicker. And it's going to be more and more Cartesian, because there's going to be less and less stretching. And I don't know if that answers the question or not. But mesh quality can affect the simulation. What usually happens if you make the curvilinear mesh too thin is that SW4 won't even start. They will complain that you can't create the mesh because it's too warped. And what happens next, if it's a little thicker than that, the time step is going to be reduced, because some cells are going to be a lot smaller than other cells. But if you follow the rule of thumb that I described earlier, and usually the time step is not restricted by what happens in the So, and there's a new question there, what's the best way to visualize throughout the 3D domain, the VTK? Well, it's true that the users have to do the post-processing. I don't have any consulting company set up yet, so otherwise I can do it for you. But we have a plugin for a code called Visit. It is possible to save not only 2D slices of the data, but also the whole 3D solution. Of course, these files will be very large, but if you have enough memory, you could do that. You probably have to work on the plugin a bit. We do provide something in the tools directory, at least a step.
So you do provide a plugin for Visit, which is also open source software. I believe downloaded through, I forgot whom.
I'm not sure. It used to be Livermore.
Yeah, it's available if you Google it.
Yes, so our plugin to Visit, I believe, only supports the 2D image files right now. So some more work is needed. Someone says the Visit is easily available. Unfortunately, it's not so easy to build it if you have to compile it yourself. That's another story. And you can send me to. Do we have any more questions? There are some more questions coming in here. More questions. If I could elaborate on how we create SRF files. Well, I think you should go to the Sketch webpage and look at the version 1 of the SRF format. I'm planning to include an example in our examples directory. Right now, by default, if you download SW4 the tarball from CIG, then there is no such example. But I plan to do that, add that soon in making it progress. The advantage of SRF files is that the whole rupture is described in one file, and they're separate from the input file. Previously, you had to put in all the discretization of your extended rupture in the input file, so then the input files became rather long. But using these SRF files, this should be able to turn it to what's the showcase application for SW4? I don't know. We have done some large-scale seismic simulations in the Bay Area, and we simulated things like the 1906 San Francisco earthquake, and we've done many scenario earthquakes that might happen on the Hayward fault.
Yeah, I think Artie's done a simulation for the Napa earthquake using it as well as you said, the through the Northern California earthquake monitor simulations on the Hayward fault.
We did simulations that were passed on to the California Academy of Sciences, and we had part of the earthquake exhibit that ran a few years ago. And there they had an SW4 simulation in their visualization dome. It was very, very well made, very well presented. And that is probably a showcase application.
Well, great. Well, we're coming to the close of the hour here. I'm going to take the opportunity to thank Anders here. You have actually one more question coming in, and then we'll cut everybody off.
Yes, you can also save fractions if you want to. There are many options in this software command, and I recommend looking at the user's guide to get all the options.
Yeah. And if you're using SW4 or you have other questions for Anders, please sign up for the SIG-Seismo listserv. We all monitor that, and you can also get support from other users that way. And thank you, everybody, for participating today. There was a lot of good questions for Anders. And we'd like to thank him and the entire development team of SW4. So if you're interested in an SW4 tutorial, please join our mailing list. That is either the SIG All and or the SIG Seismo mailing list. We are discussing offering a tutorial in 2016, and if we do so, we will announce it through those listservs.
All right, thank you for listening.
Thank you, everybody. Have a great weekend.